Okay, so good afternoon, everybody. My name is Eleonora Barbano. I am also a PhD student under the supervision of Professor Sarah Buzon at the University of Würzburg in Germany. And also my project is funded by the IRC Starting Grant. And today I'm really glad to present you the actual status of my PhD work, which is in which I'm investigating high energy neutrinos from blazars with a likelihood analysis of the IceCube observatory data. So I will be really light on this slide because I think that it's pretty clear now, thanks to the lecture done today and the last talks, why we are so interested in studying AGNs and also blazars as candidate sources for high energy neutrinos. So I will skip this introduction slide. Just a few words about the experiment instead. So, there are several experiments in this moment in data taking for astrophysical neutrino events in the world, but for sure, the IceCube Neutrino Observatory is the one with the highest sensitivity, and is basically exploiting the charge and current interaction for the neutrino detection. So we have neutrinos that are interacting with nuclei of the ice. In this charge and current interaction, there are produced some charged particles that travels at a speed higher of the speed of light in the medium, and they emit this peculiar blue chunk of light that can be detected by the photomultiplier tube of the optical sensor in the strings of the experiment, which is a massive experiment that is composed by 86 strings that stand in the ice for almost 3 kilometers. Also, a few words about the neutrino data, because for the peculiar position of the IceCube at the southern pole, basically the events that are coming from the north have a different features between the one coming from the south. In fact, the northern data, the northern neutrino has to cross the section of the Earth, so they can interact with the Earth itself, that can shield them in a way which is proportional to their arrival angle and to their energy. While the event coming from the southern sky, well, they can just interact with the Earth atmosphere. And for this reason, from the south, we have a larger background rate. Okay, so we are really interested in finding a possible link between AGNs and astrophysical neutrino events. So to do this, we have to build a very robust and also well-known, not only by IceCube, but by all the scientific community, analysis framework, which is the maximization of the extended unbinded likelihood. So first of all, what is the likelihood? Well, the likelihood here expressed by this formula is the joint probability density function F to observe xi event of our dataset N under some parameters of the assumption. First of all, why we want to maximize this function? Well, because the closer these parameters theta are of our assumption, of our hypothesis, are to the real one theta star, the larger will be the likelihood value. Why then is called extended? Well, because in all the experiment in which the number of neutrinos detected, like IceCube, follow a Poisson distribution, the likelihood can include this formalism, and the formula becomes this one. For the unbinded, I will by now skip this technical part, but if you're interested, we can discuss about it after in the Q&A part. So now that we have our formula here, the goal is that we want to test in different positions in the sky the validity of two possible hypotheses. We have the hypothesis 0, all null hypothesis, and the hypothesis H1, signal hypothesis. And for each of them, we are going to construct the correspondent likelihood function. So let's start with the first one, the null hypothesis, H0. So what is our assumption in this case? Well, that in that region in the sky that we are taking into account, we are assuming that there is no astrophysical neutrino source, but only background. So the likelihood becomes just the joint probability density function of the background. What is the counterpart now? What is the other assumption? The signal hypothesis, or H1. So we are testing the assumption that in the same region in the sky, there is not only background, but also something else that for us is an astrophysical neutrino point source that emit with a certain number of neutrino of signal, a certain number of neutrinos of signal ns according to a power law with spectral index gamma. And for this reason, this formula of the likelihood for the signal hypothesis H1 is the joint probability density function of something which is a mixture of the background probability density function and the signal. Okay. So now the goal is that we want to maximize these quantities, and then we want to understand which one of the two assumptions is the most likely to be the truth. So to do this, we can construct a test statistic. Here we choose, following the Wilks theorem, the logarithmic function of the ratio between the likelihood. But this measurement, it can be really tricky because of the data distribution in function of the declination. In fact, the background has this strongly dependent on the declination that generates the fact that if we are calculating the TS near the horizon, this will have a different weight compared to the same measurement done near the poles, for instance. So to mitigate this kind of bias, we can do a step more and pass from a measurement of the TS to a measurement of the p-value, which is defined as the probability of deviation from the background, is expressed in this formula here, and is basically the integral between the TS observed and plus infinite of a distribution generated under the assumption of having only background that, under the Wilks theorem, should follow a chi-square distribution with the degree of freedom equal to the free parameters of our statistical assumption. Okay. So as I was mentioning before, this is a well-known robust approach that was already used largely by the IceCube collaboration. Here you can see the latest SKYMAP in p-value published by the collaboration. On the left part of the slide, you can see our latest reference for the Northern Sky, here released in 2022, while on the right, you can see the 7 years map released in 2017, which is also our latest reference for the Southern Hemisphere. So the most of these blue spots that you can see in the maps are basically background fluctuation, but some of them are also thought to be signal. And in particular here, I'm highlighting the position of Texas and NGC 1068, already largely discussed, because they are shown in the last year, they are highlighted by the IceCube collaboration to be really promising candidates for to be emitters of astrophysical neutrino events. So we have, again, on the left side, a reference to the article of 2018 for Texas, with which the collaboration evidenced a chance correlation between a high energy neutrino and Texas that can be rejected at the 3 sigma level. On the right, we have the article which is the reference for NGC 1068 of 2022. With which the collaboration shown an excess of 79 neutrinos with a global significance of 4.2 sigma associated with NGC 1068. So we can think that this is a promising path. That's why we are interested in studying more objects like this. Okay, so what is now my approach? What is now my project? Well, it's clear now that to conduct this statistical analysis, we need two main ingredients, which are a dataset and a tool. For the dataset, since I'm not part of the IceCube collaboration, the driver of my analysis is the possibility to use the public dataset, so the 10 years dataset released by the IceCube collaboration in 2021, so a collection of data recorded between 2008 and 2018. And for the tool, well, in this moment, there are several tools enabling a similar analysis, but they might have some limitations for our goals. So that's the reason why I decided to develop a framework to analyze this IceCube 10 years public dataset with some motivation. So with a goal to then write an open source and a user-friendly framework with the goal of guarantees the full reproducibility of my results. There are already some current stepstones done because I already implemented partially this software based on the discussed maximization likelihood technique, modeling both the spatial and the energy PDFs for both the signal and the background PDFs. So in the next slide, I will show you the preliminary results of my code. So first of all, well, with a code that is under development, we are able to produce SKYMAPs like this one here. It's a SKYMAP expressed in TS. And another important feature is that this is not a background map, because I scramble the data in rate ascension to break the astrophysical signal if there is. Is computed with a fixed spectral index gamma for a power law test source. In this preliminary test is fixed to -2 for the reason explained in the lecture this morning. Is a map in which we have a flexibility on the possibility to choose the resolution, and this one is done with the help library. We can also choose the lifetime of the experiment, and in the end, we can also simulate a power law point source for a given flux and index. This map with this feature is also can also run in a reasonable amount of time, because it was created in 4 hours. Another important part of our work is then to study dedicated regions of interest. Here you can see that again a TS SKYMAP for a close-up view region around the position of TXS here in this red cross. Here we're looking at a TS map in which, however, we are analyzing real data. So it's not a background map, but is built with the real data. This region is then studied with a flexibility again on the resolution of the map built with the VCS library. Again, in a reasonable amount of time, because it runs in more or less 13 seconds. So now the crucial part of my work, because I also want to validate the code which is under development. So I choose to do a cross-check using the open source SKYLLH framework, well known by the IceCube collaboration. So SKYLLH is an open source Python 3 tool available at this link, which is the IceCube Neutrino Observatory GitHub repository, and is a tool which is again customized for the analysis of the 10 years IceCube public dataset, again with the same well-described technique, well-known technique. So here you can see a map again around the position of TXS realized with SKYLLH with 2 degrees of freedom, so NS and gamma. So now a comparison between the 2 codes, which is the first step of my validation approach. So here you can see the code which is under development, and here you can see the comparison with SKYLLH, both with gamma fixed equal to 2. So as you can see, both the codes can reconstruct the TS best fit position here in green in the same position. Then the blazar, so the cross, and the TS best fit position are compatible in the error of the resolution of the map, which was built with 0.2 times 0.2 bin size of the pixels, and they are in an angular distance of 0.21 degrees. And here you can also see the distribution of the TS in both the maps. And as you can see, is not completely following a chi-square distribution with 1 degree of freedom, because we are fixing gamma, because of the presence of a clear deviation from the background detail that we can assume is the presence of the astrophysical signal. Just a final comment. As you can see, the 2 spots have a different brightness. Here you can see, in fact, a map which is built as the difference pixel by pixel between the SKYLLH map here and the code developed. So for sure, there are some differences that are now in phase of investigation, and that I will try to understand in the next weeks and probably months. So I want to leave you with these slides in which are written my conclusions and the perspective in short-based and long-based terms. And thank you for your attention.
Thank you, Eleonora. Questions? I had a question.
Yes.
So can you go back one slide when you showed test statistic distribution? And that's, I'm sorry, this is a bit of a technical question.
Yeah.
So I assume that these are the test statistic values from background scrambled maps where you just basically where you expect to reproduce a background distribution.
Well, I did also this test, but here are just the distribution of the two maps that are shown in the slides in which there are the real data. So, this is not background. This is the distribution of the real data map.
But the real data would give you one test statistic value, right? How do you get the distribution?
Because for each pixel I have a TS value, so I am populating. Yes, yes.
So and I guess okay. So now I understand. So you say that close to the source you get like these high TS values.
So it's exactly what we expect around the position of the excess, so not background. But something which we think is astrophysical.
Sometimes in IceCube we also see deviations from Wilks theorem, this one-dimensional chi-square for other reasons. That's, I mean, limited statistics, for example.
Okay. I mean, I choose Texas.
Maybe you can also like look at an off-source region and try to.
Yes, is everything under development? Yes.
Okay. Any other questions?
I was wondering what the limitations are of the IceCube analysis tool, such that you had to develop your own, because I guess that's a lot of work.
Yes, it is. Yes, first of all, well, SKYLLH is an open source code, as I was saying before. But there's also a tutorial which can be followed. This, for instance, is not present in other tools that are available online, but they are more cryptical, I would say, to be understood. In SKYLLH, we can follow a tutorial. The main problem in this moment is that for a single point source analysis, so let's say that we are looking at just one pixel in the map, it requires, following the tutorial, more or less 30 seconds. So if we want to do an intensive analysis from a statistical point of view, in which you have to calculate this value for a lot of regions in the sky, it's a bit difficult by now to be used. So that's
because of computation time.
Basically, yes.
Okay.
For what we know, at least, because I mean, we are not part of the IceCube collaboration. So
okay, thanks.
Okay, other questions? Somewhere, yeah.
So you said you're developing SKYMAPs as well?
Yes.
Are they available, or where will
Not
they?
yet.
Okay, where will you like post it?
Well, it's a lot of work that has to be done before the releasing the code, but is giving us a promising results. So I cannot tell you. I mean, it's coding, so I cannot tell you the amount of time. I hope as soon as possible.
Okay, let's thank Eleonora for her time. And